Hello students, we are going to discuss something very important about benzene, and today's topic is about the benzene's electrophilic substitution reactions. And you must know about the benzene and its aromaticity before we start something new, and I'm not going to recall you, make you recall again. So when it comes to benzene, it undergoes actually two kind of reactions. The first kind is about the benzene molecule, and it never comes back again. When we are treating benzene molecule with a kind of substance or with any other substance out there, the product is not the benzene molecule or some derivative of the benzene molecule. They are completely different from the entities or the parent entity, that is benzene. In these reactions we normally consider that the benzene ring is not retained. It means it's not going to be back to the benzene ring, or it will never appear like the parallel or the alternate double bond condition which are in conjugation. And second type of reactions are those in which the benzene ring is retained and it gets back to its own identity, its original identity. And when I talk about the benzene ring which is retained, I just mean to say that benzene ring gets its aromaticity back. And what we normally consider the aromaticity is the stability of a compound, or it gains some stability just by conjugating its lone pairs or conjugating its pi bonds, the pi electrons, which is like when we draw some benzene, we normally like to write some pi bonds in alternate position. These are the alternate position. If we shift this one to the this side, this one to the alternate side, and this one to the alternate side, it's gonna be like some another molecule which actually is a kind of isomer, the position isomer. And in that isomer molecule, the benzene ring has changed its identity with respect to the position of the pi bonds. This has been shifted to the right side, this has been shifted to the right side, and this actually left. So this is what we get. And if we just change the identity again, right, so we are gonna have the same molecule from which we derived this molecule. This molecule, I'm talking about the first molecule. This is the first molecule and this is the second molecule. So one and two are completely interconvertible. This is what we normally consider benzene. Basically is aromatic compound, and what aromaticity is the stability gained by substance by conjugating its pi bonds, lone pairs or pi bonds or whatever it is present in the molecule. The equivalent structure can be written as a ring within a ring, right? So this ring is actually the center, the circular ring is actually showing you that the pi bonds are in continuous rotation. As we can see, the one is being transformed into two, and the two is being transformed back to the one. This is called the aromaticity of the benzene ring, and we are going to discuss some reactions in which the benzene ring actually retains its identity or the entity, which is the aromaticity. And these are the reactions which are called electrophilic substitution reactions. There's a reason why we're calling the electrophilic substitution reaction. We could have called something else. Uh, to know this phenomena or to identify why we are calling this as the electrophilic substitution. An electrophile is basically a kind of charged particle. Charged particle. This charged particle basically has a positive charge. And this positive charge is basically a kind of a species which you must have encountered with the sodium positive, potassium positive, calcium positive. These are all the electrophiles. You must have seen them in the reactions up till now. Well, the electrophile is being substituted on the benzene ring, but the point here is, what is an electrophile on the benzene ring? What we know about the pi bonds which are in conjugation, the pi electrons, the electron contain the negative charge. So where is the positive one? The positive or the electrophile in case of benzene, that is the hydrogen molecule, hydrogen atom. For example, when we are writing this formula, it means we just have written carbon, 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 and carbon. The whole word is carbon. Well, and we are writing the pi bonds like this way. If you just count the number of bonds of this carbon atom, I'm actually talking about, you can't see what I am just marking because you can't see the cursor. So I am talking about this carbon atom. So if you just focus, it actually contains two bonds on the left side, one bond on the right side. And this is the same configuration for all of the carbon atoms right here in the benzene ring. So it means they all have one valency that is free, and that is basically associated with hydrogen. So that is the reason we are calling carbon hydrogen ratio equivalency and benzene molecule. So there are actually 6 carbon atoms. At the same time, we are actually having 6 hydrogen atoms. The formula is there for C6H6, right? So we are not writing any hydrogen on the molecule, but it's completely dependent on what you think about the benzene molecule. If you are going to involve uh, all of the hydrogens, you can draw all of them. If you want to engage one of the hydrogen to the reaction, you can draw one of them. So it's totally up to you whether you want to draw all of them or just one of them. So this is basically the structure or the features of molecule we are going to study today. So these are the structures and formula of benzene. So you just have to keep in your mind that we are actually having something very different in the mechanism phase, and the points to remember when you're writing a mechanism are: the first point, carbon is tetravalent. Carbon is tetravalent. It means it has to form 4 bonds at the same time. Just in case, if it forms less than 4 bonds, it contains a positive charge. This is what it becomes in electrophile. So I just write carbon, which is we normally consider if an element forms 4 bonds at a time, it is called tetravalent. So if it forms 3 bonds, that will be trivalent. So carbon which is trivalent is positive, right? Positive means why do we consider the positive charge on an element? It has given up its electron and it has become deficient, electron deficient. It has lost 1 or 2 or 3 electron. Like when we talk about the calcium, it has lost 2 of its electron. It becomes the electron deficient. So positive means it has become some electron deficient center. So electron deficient centers are always positive. The last point, carbon tends to form 4 bonds at a time. It means if the carbon is tetravalent, it's completely okay. You should be okay with the carbon tetravalent. The second point, carbon can be trivalent as well. So it's gonna lose one of its valency. Like I just said, we are gonna lose some hydrogen in case of electrolytic substitution. So that becomes the trivalent, and it will contain a positive charge, which becomes the electron deficient center. So it will be requiring some electrons from the neighboring atoms. And the last point is the carbon tends to form the 4 bonds. So at the end, you are going to reflect these 3 points into the mechanism. And I just want to tell you that each time you are encountering with the mechanism, you are actually dealing with a different first step, but the second step of the mechanism of every mechanism of electrophilic substitution reaction remains same. So there is a science, because when you are just talking about the electrophilic substitution reactions, you are actually having the same second step each time, just by changing some basic parameters. And what are those basic parameters that are the part of your mechanism? So when it comes to the mechanism, you remember these 3 points, and we are going to start mechanism. Keep in your mind the negative always attack on a positive. I should write it again. The negative atom attacks on the positive one. The negative can attack on a positive. A positive can never attack on a negative atom. So this is not a possible case. So when we talk about or the negative or positive replacement reactions, you must have learned them in the beginner level. The double displacement, single displacement. These are the reactions involving the positive and the negative replacement reactions. So we don't have any other negative than the electrons, which are actually present in this electronic cloud. I'm talking about this electronic cloud. I should mark it. This electronic cloud. This electronic cloud. If you can see this, what I'm writing on screen, this is an electronic cloud, or you can also call them the electrons which are actually negative. And these pi electrons are actually free kind of electrons. They are forming some kind of delocalized orbitals, delocalized electronic cloud, like as you have seen in the metals. They are forming some electronic cloud around the nuclei. So this is the same case. You are going to deal with the negative, and the negative right now are the pi electrons. So these pi electrons are going to behave as a nucleophile. So we always wonder that how can we start reaction if we are not having any kind of nucleophile. So in case of benzene, the nucleophile is there. It's always there. You just have to watch it. That is your pi electron cloud. So one of the pi bonds is actually starting the reaction by attacking on an electrophile that is positively charged. So by describing, just order to describe the basic mechanism, I'm just starting this from the benzene, right? And I should write the alternate pi bonds. Keep in your mind that this E positive is basically an electrophile. An electrophile. Actually, this terminology, the electrophilic is basically representing some kind of substitution of the electrophile. Electrophile is a positively charged atom, right? Atom, molecule, sorry, atom. So the reaction starts from this point when the electrons, which are actually negative, attacks on an electrophile. So you can just keep in your mind that like this one is a kind of a stick, and I must show you from this point the bond is broken, and that is connected to the E. So this bond must be shifted like this way to the E, right? So this is basically detached from the lower bottom side, and that is connected to the E, right? So this is gonna happen. I'm doing it, so I just don't want to spoil my mechanism, right? So we just want to draw a mechanism, and this is how we are gonna do it. So this is attached with the electrophile. This is the bond detaching from the lower bottom side and attaches itself to the electrophile, and the rest of the bonds are appearing in the same positions they were. At this point, I just want you to recall yourself with the benzene structure, which actually contains 6 hydrogen atoms. All are the same. So I did not mention any of the hydrogen. You can mention the hydrogen or that hydrogen you need. So I need this hydrogen to be mentioned here just in order to let you know that we are actually having some positive carbons in the ring right now. So this is the carbon actually having 4 valence. right? But if you just consider this carbon atom, it actually has a bond upwards, a bond downwards, and the third bond must be connected to the hydrogen atom we already talked about. The third bond will be connected to the hydrogen. Actually, this is the carbon atom which I talked about in the important point to remember, the carbon number 2, which actually is trivalent. So this is the carbon which is actually trivalent. If you can see it again, upward, downward, and one which is not appeared here, that is hydrogen. So it actually has three valency. This is called the trivalent. So it must be a positive electron deficient center, so it must acquire a positive charge. So I am just removing these things. Just keep in your mind what I just written on screen. I'm going to remove this thing by undoing it. Why doesn't it work? Okay, so this is a carbon which actually has a positive charge, so I should mark that with a positive. So you just need to keep in your mind that if you're placing a positive charge, that must be acquired by the corners, not with the walls. I did not write this charge on the wall, I just wrote that charge on the corner. So it means the carbon which is at the corner, like this one, actually acquires a positive charge. So positive charge cannot occupy any of the space between carbon atoms. So it has to be on the carbon, exactly, right? So this is a point you should also remember. I did not mention that the point to remember. You should remember that carbon occupies a positive charge, and that positive charge should be mentioned on the corners rather than on the walls, right? So this carbon becomes electron deficient. It keeps asking for the electron to the neighboring atoms. This one is not going to give any kind of electron to it. So this left side, if you can see this, I should mark it. Why I just forgot. This carbon atom and this pi electron cloud will shift to the right side, like this way. So this is going to shift on the right side. So this is actually shifting to the wall, not to the carbon. I should mention it more clearly. It is shifting to the wall, not on the carbon, right? So you should also remember the point. I did not mention that too in the points to remember. Well, the bonds are shifting to the walls, making it something different. The same structure, which appears something different, is we just need to change the positions, not with the electrophile or the hydrogen, but with the pi bond. So this appears here, and this appears here. So if you just consider that we are having another carbon, which is actually electron deficient, the positive sensor this time, if you can see the number of bonds upward, downward, to right, and the last one that is connected to the hydrogen, I did not mention that. So it actually has three bonds, and it must be acquiring a positive charge. So the positive charge actually delocalized itself from the right side to the left side. So I'm going to write it on this carbon atom. Once again, I'm repeating, the carbon occupies a positive charge. It actually has a positive charge, but on the corners, not with the walls. So the same thing which has already happened in the step number 1, this pi bond shifting to the right, to the electron deficient carbon. So another thing happened at the same time. This pi bond shifts to the left side. Repeating again, the pi bond shifts to the wall, not to the carbon. And if you are just seriously concerned with the arrows, I should mention them more clearly, right? So this is shifting to the left side wall. And what you can consider from the previous steps, that we are going to have a different benzene structure which actually has a positive charge, delocalized again this time. So this is the pi bond number 1, and this has changed its position to here, and the positive charge is right now has been shifted to the first carbon, or the topmost carbon of the benzene ring, right? So this is what has happened. If you just consider without writing the positive charge, or before writing it, I should mention it again. that this carbon actually has some two electron right and left, and the last one will be connected to the hydrogen, making it trivalent. So this is actually the center, the electron deficient that contains the positive charge. So that was the reason I've drawn the negative for positive charge, right? So right now we are just dealing with the energy situation. Like when you talk about simple compounds, they appear like the NaCl, MgCl2, MgO. For any of the compound, for all of the compound actually, what is similar? All contain a positive and a negative side, irrespective of the nature of charge, either ionic, covalent, or the number of charge. We are just having some molecules, some atoms, which are actually having some positive and negative charges. So it means the point or the compound from where this electrophile comes, electrophile. So the point or the compound from where this electrophile comes actually has a negative thing which is called a nucleophile. We have already studied about it, and that is basically represented as Nu negative. So we must consider, for example, NaCl. In case of NaCl, if Na is the electrophile, right? Na is the electrophile, and Cl must be the nucleophile. So for every electrophile there is a nucleophile, Na positive and Cl negatives. Likewise, the compound from which the E was drawn actually has some negative. And right now we are going to deal with that negative, because we know that the negative actually attacks on a positive. If you just focus on this point, the negative attacks on a positive. So we are having the nucleophile that has come from the same compound the E positive came starting of the reaction. Since it is a negative thing, it must attack on the positive thing. Right now, to end up the mechanism, you need to know, or you should remember when you are writing mechanism of electrophilic substitution, that the positive charge, I should mention, I am talking about this positive charge. This positive charge was actually replacing its position all the time, right? So for every time it changes position, a nucleophile comes but does not attack on this positive. The reason is it just try to attack on the first side, like for example the 1, it goes to the second. And when the nucleophile approaches on the second side, it has actually moved to the third one. So nucleophile can never attack on a positive charge which is actually replacing its position. So this is the reason the nucleophile is not going to attack on this carbon. I'm actually talking about carbon number 3. So nucleophile can never attack on this carbon. The reason is the positive charge is being delocalized on the entire ring. So this is not the case. Nucleophile is not going to attack on this carbon containing positive charge. So the remaining, or the positive which is left in the structure, is none other than hydrogen. Because what we know about the hydrogen, it gives up its electron easily, right? So the same thing appears in this compound. The nucleophile, that is from the negative. The nucleophile attacks on the hydrogen. Since it gives up the electron, just keep your eyes on how I am going to write the bond shifting or the electron shifting. I am writing these electrons are shifted inside the ring this way, right? So the electron pair, complete electron pair, the pair of the electron or the entire bond you can see is actually shifting inside the ring this way. So if we just drive a molecule like benzene, and we are just going to drive the previous 5 bonds, it appears in this wall. So are we having some alternate double bonds? This will regenerate its aromaticity. So this was the concept. The benzene ring was actually retained in aspect of the aromaticity. So when it gets back its aromaticity, it means the benzene has been retained in the structure, in the mechanism. So Hydrogen goes with the nucleophile, makes something else. We are not concerned with the compound. That may be H and U. For the convenience, we are writing the formula. The last thing, the benzene has something in it, is the aromaticity, right? So it has been generated. The final thing, when you are writing the structure, keep your eyes that I just mentioned the both sides. What I've done, I have just mentioned the double-headed arrows on the both sides. It means these structures are interconvertible, but I did not mention that in this arrow because a reaction was actually initiated this way, and I did not write even in the last one. It means the reaction ended up. So in between, the reaction was actually propagating to and fro, or producing something that is actually delocalized positive charge. So we are gonna write these things in some brackets to make it sure that we are talking about the structure which are being formed and contains a delocalized positive charge, just in order to restrict them or to bound them, right? This is the structure. I'm talking about the structure, this one, which have formed in between, are called adenine complexes. I left it. I thought it was paused. Sorry. Sorry for the delay. I can't cut it right now because I'm not aware with the software. Maybe I'll be doing it soon. Well, this is called the adenine complex, and this has to be formed by the attack of this pi bond to the electrophile. So what we normally consider, this is the structure of the basic mechanism. So every time or each time you are going to deal with a different case, you are actually changing this entity, not with the entire mechanism and this entity as well, right? So we are going to discuss some different concepts or some different reactions in the benzene. We will talk about it. You can find in the description the PNG what I've just written on the screen.